Okay, so the notes for solving logarithmic equations. So logarithmic equations are equations that involve logarithms of variable expressions. You can use the next property to solve some types of logarithmic equations. So the property of equality for logarithmic equations is very similar to the exponential one. So if b, x, and y are positive real numbers with b not equal to 1, then you're going to see log base b of x is equal to log base b of y. Since they both have the same base of b, just like before, we can cross these out. And now the argument, x and y, should be equivalent. So x equals y. And I'm assuming y if and only if x equals y. So the example they give us here is that log base 2 of x equals log base 2 of y. So once again, I could just cross these out since they have the same base, and it's 1 logarithm equals 1 logarithm. So x equals 7, which we see right there. All right, so let's take that property and apply it here to 1 and letter A. So I have a logarithm equals a logarithm, and they have the same base. So I can cross this out. And I'm going to solve the argument. 4x minus 7 equals x plus 5. I like to bring my variables to the left side, so I'm going to subtract x. Now I'm going to move my constant to the right, so I'm going to add 7. So 3x is equal to 12, divide by 3, and x is equal to 4. Now, when you are doing this, what you're going to want to do is you're going to just plug this into here and make sure it is positive. And it should, for the most part, be correct. You can definitely plug it into your calculator, double check it, but that's what I tend to do. 4 times 4 is 16. 16 minus 7 is 9, so that's like log base 5 of 9. And then 4 plus 5 is 9, so log base 5 of 9. So log base 5 of 9 does equal log base 5 of 9. All right, for the second example, we have ln, which we hopefully remember that ln is log base e. So ln of 7x minus 4 equals ln of 2x plus 11. Our logarithms are the same, so we can cross those out. And now we have 7x minus 4 is equal to 2x plus 11. Just like before, I bring my variables to the left side, so I'm going to subtract 2x. I'm going to add 4 to the other side to isolate my x. Divide by 5, and x equals 3. Double check it. 7 times 3 is 21. 21 minus 4 is 17. 2 times 3 is 6. 6 plus 11 is 17. So ln of 17 does equal ln of 17. That checks out. All right, for the next ones, exponentiate each side of the equation. All right, so in this case, we don't have logarithms on both sides. We have a logarithm equals a constant. So in this case, what we're going to do is we can't just magically make up a log base 4 here because we have to balance it. So if there's a log base 4 here, then we would have to, if we put a log base 4 here, we'd also have to add another one here. So it'd be log base 4, which makes no sense. So here's what we're going to do. We are going to apply that property I talked about. So we're going to create inverses. So we talked about if you have a base b raised to an exponent that's a logarithm with a base b, this creates an inverse here, so you can cross those out, and your answer is the argument in the exponent, which is x. Okay. So in this case here, I look for the logarithm. So the constant is there. This is a logarithm. And what I'm going to do is I'm going to add a base b to each one of these. So I'm going to start with 4 raised to the log base 4 of 5x minus 1 equals 4 to the third power. So notice they now both have a base of 4. And what we have done here by doing this is created an inverse. So base of 4 raised to log base 4 inverses, so we cross that out. And we now have the 5x minus 1 equals 4 to the third. And 4 to the third is going to be 64. And now we just solve it. Add the 1. 5x is equal to 65. Divide by 5. And x is equal to 13. Okay, so we can always plug this here. 5 times 13 is 65. 65 minus 1 is 64. And so log base 4 of 64 does equal 3. You can double check that in the calculator if necessary. All right, let me try the next one. So the same thing, we have a logarithm that equals a constant, so I just can't add log base 2 there. So I'm going to exponentiate it by adding the same base. So the logarithm has a base 2. That is what I will use for both of them. Inverses, so x minus 6 equals 2 to the 5th, which is 32. Add my 6, x equals 38. You can plug that back, double check it, and it will definitely work. All right, and now we're down to the last examples here. So it says solve the equation, check for extraneous solutions. So recall, extraneous solutions are just answers that do not satisfy the original equation. So this is a little bit different now because we have two logarithms being added together equal a constant. So in order for us to actually solve this needs to be condensed to one logarithm. And if you recall from properties of logarithms, whenever we have two logarithms with the same base being added, all we actually do is we multiply it. So it's going to be log of 5x times x minus 1 equals 2. So now I'm just going to distribute this 5x. So log of 5x squared minus 5x is equal to 2. Now, when there is no base, that's called a common logarithm. So we understand the base is 10. So we're going to do a base 10 on both sides. From here, we can cross these out because base is 10. So we have 5x squared minus 5x equals 10 squared is 100. Last, we bring this over to the same side because it is a quadratic function, and in order to solve quadratic functions, we have to set it equal to 0 and test to see if factoring works. If that doesn't work, we'd have to do the quadratic formula. Now, one thing before I start solving, I noticed they're all divisible by 5. So I'm going to divide the whole problem by 5, even the other side of the equation. So x squared minus x minus 20 equals 0. X method, negative 1, negative 20 on the bottom because 1 times negative 20 is negative 20. Divide by 1. And then we have a 5 and a 4. Negative 5 plus 4 is negative 1. Negative 5 times 4 is negative 20. So x minus 5. X plus 4 is equal to 0. When you solve them, set each one equal to 0. X is equal to 5. X is equal to negative 4. Now, checking for extraneous solutions, just like before, we're going to plug it back into the original. So we start with this 5 here. 5 times 5 is 25. That's positive, so that's going to work. 5 minus 1 is positive 4, so it looks like this is going to check out. You can always double check by typing in the calculator, make sure it does work. Now, negative 4. 5 times negative 4 is negative 20. You cannot take the logarithm of a negative number. Therefore, this is extraneous. All right, let's take a look at this last example here. Log base 4 of x plus 12 plus log base 4 of x is equal to 3. So here, once again, we do have that plus sign, so we're going to condense it this time by multiplication. Here, I'm not going to write out that other step. I'm just going to multiply it. X times x is x squared. 12 times x is 12x. Don't forget my base of 4 equals 3. So we have this base 4 here, so we're going to add a base 4 for an exponential function to each side of this equation. So this cancels. We have x squared plus 12x equals, we already know 4 to the third is 64. All right, from here we're going to bring the 64 over. Since it's a quadratic function, we need to set it equal to 0 to solve it. X method, 12, negative 64 dividing by 1. Factors are going to be 16 and 4. And this will be minus 4. All right, 16 divided by 1 is 16. Negative 4 divided by 1 is negative 4. X plus 16 equals 0. X minus 4 equals 0. X equals negative 16. X equals 4. And don't assume the negative 1 is automatically extraneous. You do need to plug it in and double check it. But negative 16 plus 12 is negative 4, which is extraneous. The 4 plus 12 is 16. 4 is there, so this one should check out to be good. Always plug them into the calculator to double check, but this looks good.